Going back to the electric fields for a second, we know that, charged particles create electric fields, and electric fields create forces on charged particles. We know that magnetic fields create forces on moving charges. So it might make sense that moving charges create magnetic fields. And that is exactly right, they do. We could determine the magnetic field created by a single moving point charge, but that is a very, very difficult way of determining magnetic fields. We will assume that we have a long, straight wire, and we are looking at some point near the wire. Now, what do we mean by near the wire? How near do we have to be? We have to be near enough to the wire that the length of the wire is much larger than the distance we are from the wire. In other words, this distance that the wire continues straight up and this distance that the wire continues straight down is large compared to r. In other words, the wire looks like it's essentially infinitely long. Obviously, wires are not infinitely long, but we are approximating it by an infinite wire. So we need to be close enough to it that the top and the bottom look like they're going off into infinity. If that's the case, the current creates a magnetic field at this point R, and the magnetic field is proportional to the current. The more current we have, the more magnetic field we have, the stronger the magnetic field. We might think that it would drop off like 1 over r squared, kind of like the electric field drops off like 1 over r squared for a point charge. However, this is not a point charge. It is an infinitely long wire. So the magnetic field does not drop off as 1 over r squared. It drops off less quickly. It drops off as just 1 over r. We can actually write this as an equality. It turns out that B is then equal to I over R with a constant of proportionality. If you'll remember, for Coulomb's law, our constant of proportionality we wrote as K, but that could also be written as 1 over 4 pi epsilon naught. Well, the constant that we'll use for B we'll actually write as mu naught over 2 pi. So the combination of constants that we'll use for our preliminary constant here is mu naught over 2 pi, where mu naught, if you'll remember, epsilon naught we call the permittivity of free space. Mu naught is the permeability of free space. Permeability of free space. And it has a value. This is kind of a peculiar form for a constant, but it equals 4 pi times 10 to the minus 7th. And in order for the units to work out right, they are Tesla meter per amp. Tesla meter per amp. 4 pi times 10 to the minus 7th Tesla meter per amp. It's essentially a way of defining what an amp is, what a certain measure of a current is in terms of the magnetic field. And remember, the magnetic field we have defined in terms of newtons and charges. So it's a way of defining how much an amp is in terms of those magnetic fields. Excellent. Let's stick some numbers. Oh, I'm sorry, one more thing. What's the direction of the magnetic field? This is another application of the right-hand rule, a slightly different application. For the wire, to determine the direction of the magnetic field, the direction actually goes around the wire. It doesn't point away from the wire like you might think the electric field points away from a charge or towards the charge. A magnetic field actually goes around the wire. And it goes around the wire. If the current is going up, it goes around the wire this way. It comes around and goes around this way and goes around behind the wire that way. Whoops. So around the wire this way. we can use the right-hand rule by pointing your thumb in the direction of the current. Your fingers will then wrap around the wire in the direction of the magnetic field. If the current were going downward, point your thumb downward, the magnetic field would wrap around this way. So that means for a current that's going up, the magnetic field will go into the board over here, out of the board over here, this way in front of the wire, and this way behind the wire. If we had a current going downward, then the magnetic field would come out of the board on this side, into the board on this side, and go to the right behind the wire and to the left in front of the wire. So we've got to be a little bit careful in thinking about the direction of the magnetic field for a wire. Let's stick some numbers in here. Let's imagine that we have a current pointing downward with 3 amps. And we want to determine the magnetic field at this point over here 2 meters away from the wire. And we're going to assume it's essentially an infinitely long wire. A very long wire, much longer than 2 meters, both upwards and downwards. Let's figure out what's the magnetic field at that point. We have that B is equal to mu naught over 2 pi times I over R. Mu naught, remember, is 4 pi times 10 to the minus 7 Tesla meter per amp, divided by 2 pi times I, 3 amps, divided by R, 2 meters. And what do we get? Well, let's notice we have pi and pi cancels out. We've got 2 and 4 cancels out, leaving us with 2. 2 and 2 actually cancels out. You could actually do all of this on your calculator if you wanted, but it would all cancel out. We've got amps and amps canceling out, meters and meters canceling out, and so what are we left with? We are left with 3 times 10 to the minus 7th Tesla. There we go. That is the magnitude of the magnetic field. 3 times 10 to the minus 7th Tesla. What's the direction? Try the right-hand rule. See if you can figure it out. What's the direction over here? Well, our thumb goes in the direction of the current. Our fingers then point in the direction of the magnetic field. It's going to curl around this way, and over here it will go into the board. So over here, the magnetic field goes into the board. So at this point, this would be into the board. If we looked at a point over here, what would be different if it were 2 meters on the right side? Same magnitude, but the direction would be out of the board. What if we were to look at the point out here, 2 meters in front? It would be to the left. 2 meters behind, it would point to the right. What if we were to come down here, just come downwards? Same distance, it would be exactly the same as this one. Up here, 2 meters. Remember, the distance is always measured directly to the wire, perpendicular. It's not measured down here to the origin or something like that. It's always measured perpendicular, whatever that distance is, perpendicular to the wire. Well, I hope that was interesting. Next time, we're going to take a look at a slightly different approach to the magnetic field. We're going to introduce a new quantity called the flux, and we'll see how there's a different interpretation that we can have.